Hello guys. Have you enjoyed ETH Seoul so far? Great. And I'm Ryan, and I'm a blockchain lead at Lightscale. And before starting, I should say that I have, maybe the organizer and Erica noticed that the presentation changed a lot. I tried to make sure that presentation, I tried to deliver the key message in a very easy way for you to understand, and because I practiced in front of teammates, and my teammates complain about it's too hard for audience to understand the content. So I practiced a lot, and I changed the presentation whole in a way to understand the key points, right? So I'm gonna start the presentation, and I'm so excited to talk about a Kroma on new layer 2 network, but I believe most of you may not have heard of Kroma before, so I prepared some questions to help you understand. So is Kroma an optimist rollup? Do you guys know? Yes. Does Kroma use zkEVM? Yes. And you can think of Kroma as a combination of optimism and scroll zkEVM. And why is that? I will tell you the reason why we combine this tag later. And I think that mixing the scroll, I think that it is very hard to integrate zkEVM into optimism. It's kind of hard to me, but in result, it's not that hard that it sounds. I tell you the modification part later, and you think that not that much part is modified in the result. So in today's presentation, I will cover these three main topics. One is that what we have changed to optimism and zkEVM circuit. And please do not fear. And as I said before, I'm gonna deliver the key points in a way that is very easy to understand. So please don't leave. And finally, I'm gonna cover why we start our chain from optimist to Rollup, and how to transition to our chain to GK Rollup in the end. So optimism consists of these 5 components: L1 contract, L2 contract, L2 node, OP-get, and Canon for fault proof. In the case of Kroma, it consists of these 5 components: L1 contract, L2 node, Kroma-get, and zkEVM. And for our purposes, we have mainly changed these 4 green highlighted parts. But today, I'm gonna talk about these 2 highlighted parts. So let's go to the change to optimism. So before going deep dive into what we have changed, let me show you how the optimist rollup works. In this diagram, which I taken from the optimism blog, it says it is composed of L1 and L2. Rollup uses state transition function, for short, STF, to compute state or change the state, and then it submits the transaction as a batch and state commitment to the layer 1. And it shows that it seems that like the submission happening every L2 block, but in fact, the submission happens in the periodically. So many L2 blocks are bundled together and submit as a batch. So the term is rollup. And here, state commitment plays a very crucial, important role in withdrawing funds from layer 2, because if an incorrect state root is submitted to layer 1 and nobody challenges against it, the whole funds deposited L2 could be lost. So someone has to challenge against the incorrect state root. So to submit the proof, to submit the challenge, you need to run the state transition function locally, right? And to do that, you need to derive the state based on the transaction from submitted to layer 1, right? And in order to do this, so you download the transaction and you run the state transition function. And once you collect the proof and you submit the proof and challenge to the layer 1, the contract should run the proof fraud function, or more recently, we refer to as proof fraud function. The layer 1 contract should run execute at the transaction to determine the outcome of challenge. And in order to run the function, you need the two ingredients, which is, as you can see, state 2 and transaction 2, which is the previous state and the transaction for the next block, right? Please take note that we need to it is required to access both previous state and transaction. So proof for function, as I said before, you need to access to state and transaction. State is very easily to be obtained. You can obtain the state from state root and corresponding Merkle proofs. Then what about the transactions? If you take a look at the architecture of optimism bedrock, there are two submitters. One is batch submitter, and the other is output submitter. And batch submitter compresses transaction and submits the transaction as a batch and via a core data to EOA, which is called batch in box. But in the case of state root or state commitment, the output submitter submits it to the contract. But for contract to read the transaction, it is impossible for contract to read the data from core data of the previous transaction. It only accesses the data from the core data of the current transaction, right? So in order for contract to read the data from code, in order for a contract to read the transaction data to run the state transition function, we need to come up with some alternative way to do this. So we need to make a choice between either change the destination of the transaction from EOA to contract, or we need to somehow figure it out to retrieve the transaction from contract, state commitment. In our case, we don't want to increase the cost of, we don't want to increase the cost because of the challenge, because considering that challenge happens rarely, right? You don't even have a chance to watch the challenge happening in layer 2. So we decide to retrieve the transaction from state commitment. In the case of optimism, they use upload as a state commitment. They submit upload, and it is composed of version, state root, withdrawal storage root, and block cache. And nothing can be helpful in terms of retrieving transaction. So we include next block cache when computing upload. In this way, by submitting pre-images to upload, you can retrieve the transaction. So in the case of Kroma, when you submit the state commitment to the network, it contains next block cache in the state commitment. By providing transaction root and Merkle proofs and next block cache, upload, and the pre-image, now you can obtain all the ingredients to run the state proof work. Wow! So let's switch. Okay. So, and in typical optimist Rollup, there are two levels of interactions. One is block level interaction, and the other is instruction level interaction. And in the case of Kroma, we eliminate away the instruction level interaction because all we need is just the block cache, just transaction and previous state. And what even makes me more excited is about this architecture. Once the future development technology such as proof recursion is applied to our case, then whole interaction could be got away. So once you manage to success to produce a proof, you just submit the proof, and then you can know the outcome of the challenge. It's amazing, right? And I'm going to show you how the block interaction happens at our chain shortly. And before that, I'm going to define two participants here. One is asserter, and the other is challenger, to help you understand what's going on in the next slide. And asserter is the participant who submit the state commitment to the layer 1. The reason why we name asserter, because he asserts some certain state transition is correct, and the challenger is the participant who raised objection to an incorrect state commitment. So our challenge always starts with challenger and ends with challenger to make sure for him to submit the fourth proof. So in this case, challenger needs to submit this much state commitment to the network. And he needs to submit the state commitment in units of 4 ETH blocks. The reason why he submits such like that, this is because if you submit all the state commitment which is required for challenger to the network at once, it might exhaust the whole block gas limit, right? So he submits something like that. And if an asserter detects some challenge is going on, then he needs to find the first mismatched state commitment from the state commitment submitted to the network. And in this case, fourth state commitment is different. So it needs to submit the whole state commitment within that interval. And then, similarly, challenger needs to submit the rest of, needs to find the first mismatched interval and needs to submit the rest of state commitment to the network. In this way, both of them can agree with one step of single state transition, and now it's ready to run proof work function. This is how the challenge is going on in Kroma, and let's switch to the perspective of zkEVM. And zkEVM is a very complex program, even for me, but if you take a look at it very simply, it's a program to produce proof based on an input called execution trace. And the zkEVM introduced the concept called type, and our zkEVM is based on scroll, which is type 2.5, so which targets to EVM equivalent. So what this means is that if your solidity, if your contract is developed to be deployed to optimism or layer 1, you can deploy your contract to our chain without any significant change, which provide you with compatibility and ease of adoption. And zkEVM produces a valid proof only if the state transition follows EVM specification. But to zkEVM, in our case, he doesn't know about some custom parts which is derived from optimism. So we need to let him know what's unknown to him. So in this case, you can think like the 2 points are different. And one is one is the derived from custom transaction called deposit transaction, and the other is fee collection, because the L2 needs to submit the transaction to or stay commitment to the network, right? So the layer 2 needs to collect the fee from user, right? So deposit transaction differs in a way that it may mint if, and it doesn't provide a tip to Coinbase, and it computes something called source hash, and it doesn't involve in signature verification. And fee collection for transaction other than deposit transaction, it differs in a way that it collects at the base fee, it doesn't burn base fee, and it collects Rollup fee based on Aaron base fee. So we need to let him know these unknown points. And we did it very simple way. So Scroll zkEVM is based on PSC zkEVM, and they mainly have changed this red highlighted part. And in the case of Kroma, we mainly changed these two parts. One EVM circuits to handle deposit transaction and fee collection, and transaction circuit to handle deposit transaction. And the current event circuit is composed of these many circuits. It is always start with begin block step and it ends with end block step. And for each transaction, it always starts with begin transaction step and it ends with end transaction step. And to handle deposit transaction in EVM circuit, we have introduced begin deposit transaction and end deposit transaction. And to handle fee collection part, we have added base fee hook and Rollup fee hook steps. And yeah, there's not much difference, right? And in a typical transaction, it involves in computing two kind of hash operation. One hash is used to verify signature. The other is used to compute transactions root. And in case of EVM circuit, this kind of operation is handled with the way called lookup. And in the case of deposit transaction, as I said before, it doesn't involve in signature verification, and it computes something called source hash. So in the typical transaction, like transactions other than deposit transaction, we can reuse the transaction circuit. But in the case of deposit transaction, we need to replace the transaction source hash values with some parts related to transaction sign part. Yeah, that's done. With these two modifications, you can combine zkEVM on top of optimism framework without that hard engineering cost. And in the end, I'm going to talk about why we start our chain from optimistic rollup and how we are going to transition our chain to GK rollup. So we think that at this moment, proof generation cost and time is expensive and slow from the practical perspective, but we believe that GK rollup is the future. So there will come a time that to overcome all the limitations I mentioned. So we designed our chain to be easily transitioned to GK rollup. Let me show you what I mean. So does Kroma plan to be a GK rollup? Yes. And do we need a state migration? No. Why is that? Here, if I refer to state migration, it means do we need whether moving the reads from MPT to leaves of zk-friendly tree. In our case, we don't have to, because state is already represented by zk-friendly tree. So when we transit our chain to zk Rollup, there's no pause time. It could be transitioned to zk Rollup smoothly and without any halt. Amazing, right? And let me share our status and plan. So we launched our testnet in the last quarter, and we are now operating the testnet. In the next quarter, we are going to launch mainnet for Optimus Rollup version. In the last quarter of this year, we are going to launch zk Rollup testnet. And the second quarter of next year, we're going to launch mainnet for zk Rollup, facilitating the transition, the chain. Yeah, of course, there are many challenges and there are many concerns to be solved, but we are committed to solve one by one, so please keep an eye on our progress. And let me wrap up the presentation today. So I just talk about what we have changed to Optimism and zkEVM circuits. To verify for proof in the layer 1, we need to access transaction. And to do this, we modified upload so that we can retrieve the transaction from it, and we are able to run the verify function. And to let the zkEVM circuits know the custom parts derived from Optimism, we have changed mainly two parts of circuit. One is EVM circuit, and the other is transaction circuit, to let him know the deposit transaction and fee collection part. And in the end, I just said before, our chain is Optimus Rollup, but we plan to transition our chain to zk Rollup and without any state migration. Additionally, we are nowadays working on validator decentralization, because we think that in the context of blockchain, decentralization part is very important. So yeah, that's what we are doing right now, and we are going to be audit in the 2 weeks later. In the end of June, and after that, in the short term, we are going to implement account abstraction. In the long term, we also want to or plan to decentralize the sequence part using T-based PBS. So thank you for listening. If you are interested in what we are going to do, then you can follow up any links here, and you can scan the QR code. And I always be there, so you can feel free to come to me and ask what you're curious about. And thank you for listening.